Okay, cis-2-butene reacted with Br2, CCl4, draw the products, and the mechanism.
We're going to take the simplest cis alkene that we have and we're going to react it with Br2. Now notice that we use a solvent here, which makes it different than the free radical halogenation. Okay? What's going to happen here is, remember, all of the reactions we've seen before, what does the double bond do? It swings out and picks something up, right? Well, it's kind of like that, but this time it's three parts. First of all, you're right. The double bond swings out, picks up the Br, and at the same time, the Br attacks the opposite side of the double bond. And then this Br comes out. If the double bond hits one side of this Br and the Br comes in on the other side, what's it going to do? It's going to make a ring, right? Well, if it makes a ring, then you have this Br in a three-membered ring. You have this halogen, this positive in a three-membered ring. It's not going to be there very long, right? So then you have this floating Br minus, and that's going to attack one of these carbons, right? And if you do that, then that's going to break the ring and it's going to go either way. So, right, so we got A and B. If it goes the A way, then you have the BRs look like this. And if it goes the B way, you have the BRs go like that, right? So what are they? Are they enantiomers, diastereomers? Are they the same? You got to do the stereochemistry, okay? So you put them up straight, and then you do the stereochemistry. So you do 1, 2, 3, 4 clockwise R, 1, 2, 3, 4 clockwise R, 1, 2, 3, 4 counterclockwise S, 1, 2, 3, 4 counterclockwise S. So if you have RR, SS, that's enantiomers.
Trans this time. What I initially get though when I stand this thing up, and we notice that this compound here is what? Meso, so it can't have an enantiomer. Look at this compound. Again, this is the same thing because it's just a meso compound. They're the same. So cis-2-butene, end up with a pair of enantiomers. Trans-2-butene with Br2, end up with same compound because the product is meso. And now we're going to look at these same two compounds, but now we're going to treat it with OSO4. We're not going to dwell on the mechanism. Cis-alkene here. We're going to react this with OSO4 H2O2. This is going to put basically two hydroxyl groups in from the same side. And over here we have our two OH groups. And what do we notice about this? This is meso cis-2-butene. We get only one product. As opposed to trans-2-butene, that what we're going to get is two products out here. This yields now a pair of enantiomers. Call it a dicarbonyl compound for short. Where do these dicarbonyl compounds come from? Well, we look at the two carbons that are involved in the C double bond O's. We count the number of carbons there, and it turns out to be 5. So our precursor molecule has to be where those two carbons were connected back together. So now we have cycloalkene. Where do cycloalkenes come from? Haloalkanes. We draw the CH3 and the Br on the same carbon. Where do haloalkanes come from? Alkanes. Methyl cyclopentane. Now this becomes the hard part, how to take off this methyl group. We can use an organometallic where we had the ring, negative carbon there, Li plus, organolithium. These come from haloalkanes. I'm just going to put a Br right there. Haloalkanes come from cyclopentane, cycloalkane. Now our retrosynthesis is done. And look in the forward direction here, Br2 and light, 2Li, CH3Br, simple SN2 reaction, Br2 and light, E2 now, that's a tertiary. I just put a charged base. Notice again, we're ending with an aldehyde here. So this is going to be ozonolysis instead of the permanganate O3 ZN H2O. When you're doing a multi-step synthesis, write down what you've got and think of the functional group that it comes from. And keep thinking back one functional group at a time until you get back to your starting material. After you do the multi-step in reverse, this disconnection, then put in your reagents in the forward direction. This is a diol. Di meaning two, ol meaning alcohol. Comes from alkene again, cyclo. Where does that come from? Halo, alkane. Bromo, cyclo, pentane. Back to alkane. In the forward, Br2 and light. Now we have a secondary halide, and I need the alkene, NaOH, OSO4, H2O2. OS for osmium, remember, okay? Dihaloalkane. And where do these come from? The alkene, haloalkane, which comes from alkane. Alkane to haloalkane, Br2, light. We have the Zaitsev product here from the secondary. So this would be NaOH. Two BRs added across the double bond in an anti-fashion. This is now Br2 in an organic solvent, CCl4. Now the difference between 1,2 and 1,4 addition, we have to realize that in the first part of this mechanism, we have this 1,3-butadiene. And the first thing that has to happen is this has to react with HBr. When it does so, the pi bond will swing out, pick up the proton, and liberate Br minus. So what we get is something called an allylic cation. So here's my allylic cation. Well, you have to realize that this thing can exist in one of two resonance structures, the way it is right there, and it also can exist like this. This structure will yield you the 1,4 product, where this structure will yield you the 1,2 product. Now, it says here at minus 80 degrees, which is very cold, we get predominantly 1,2 product. The reason for this is a couple fold. EA12 is less than EA14. Therefore, it's a smaller hill, and it's easier for the reaction to go over that smaller hill. So at minus 80 degrees, you only have enough energy, for the most part, to get over the smaller hill. We call this kinetic control. And the reason we call it kinetic control is because, like it says right here, this product just forms faster because you have a smaller hill. But we notice at 40 degrees Celsius, things kind of change. Now, why are we getting 1,4 as the major product? The first thing we know is that we have enough energy for EA14. The second thing is 1,2 product can reverse to intermediate. And 3 is the 1,4 cannot reverse.